Hi everyone, I am Dr. Hang Ding from IU South Bend. Welcome back to my lecture of programming in Go. This lecture is the third part of topic 1.1 basic components of a Go program. In this part, you will learn about strings and Unicode characters in Go. You probably already know what a string is in other programming languages such as C, C++, and Java. A string is typically defined as a sequence of characters in other languages. In Go, a string is an immutable sequence of bytes. The built-in function len takes a string as argument and will return the number of bytes in the string. For example, suppose we define the string S to be the string literal hello world, and when we print len of S, so it returns 3. Okay, so it will show the number 3 because there are 13, not 3. Because there are 13 characters in the string hello world, including the comma, the space, and exclamation point. You can retrieve the byte at a given index in a string using the index operation, which is denoted by square brackets as in arrays. In particular, to retrieve the byte at index I of string S, we write S, then open brackets, then I, then close brackets. Okay. And so in particular, you can enter any index between the two square brackets in order to retrieve the byte at that index of the given string, which is written immediately before the open brackets. Note that the index operation can only be used to read data stored in a string. Since strings are immutable, you cannot modify their data. For example, if you try to assign a value to S of 0, where S is string, so then you will get a compile error because you are trying to modify the byte at index 0 of the string S, and which is forbidden. In addition to the index operation, there are many other operations on strings that make it convenient to handle strings in Go. One of such operations is the substring operation, which is also denoted by square brackets as in the index operation. But unlike in the index operation, the substring operation will take a range of indexes instead of a single index inside the square brackets. A range of indexes is written as two indexes separated by a colon. If S is a string variable, then S of I colon J, where I colon J is written between the square brackets, use a new string consisting of the bytes of the string S starting at index I and ending at index J minus 1. So J, or the index after the colon in the substring operation, is one index over the last index of the substring. For example, suppose variable S is defined as the string literal hello, comma, space, word, exclamation point. Then when we write S of 7 colon 12, Then we get the substring of S from the index 7 until the index 11. And the character at index 7 in the string S is character W, or the byte corresponding to the ASCII character W. And the character or byte at index 12 is the exclamation point. So the substring of S 7 to 12 is just the string word from the string hello world. Another operation on strings is concatenation, which is denoted by the addition or plus operator. The addition operator makes a new string by concatenating two strings in its operands. For example, the addition between the string literal by and the substring as of 7 to 12, which is the string word, yields the string by word. Recall that the addition operation has the corresponding shorthand assignment operation denoted by plus equal. Note that this assignment as plus equal and the string comma space by does not modify the string that the variable s originally held, but it causes a variable s to hold the new string formed by the concatenation. String can also be compared using comparison operators such as equal, larger than or equal, or less than, etc. The comparison is done byte by byte between the two strings being compared. Okay, so here is a program that demonstrates the operations on a string. The first line here is to declare the variable s to be a string, and s has the value which is a string hello world, and then we try to print out the substring of s from index 7 to index 11. Okay, so we have to write 7:12 because the second index must be 1 more than the last index of the substring. And then we try to print out the addition of the string byte to the substring and the substring of s from 7 to 11. Okay. And then after that, we will assign s to be a new string that is equal to s plus the new string comma space by. And so now we will print out the string s to see whether it's the same as the original one. So now let's run this program. And so here's the result. Okay, so here this one is the substring s, so which is word, and then this is the result of by plus the substring of s from 7 to 11, and the last one is the content of the new string that the variable s is holding. Okay, so now we also try some comparison between strings. So let's try to print out the comparison between s and the string, the original string hello world. Okay, so we are using just the equal size, and so then we also try to compare s, whether s is larger than or equal to hello world, and also whether s is less than or equal to hello world, and then click run. Okay. Is compiling, and we are waiting for remote server. It's a little bit slow. Okay, so in this case, we have to run again and see. Let's see. Okay, so we still have the error communicating with the server. Try again. Okay, so here we go. So the first one is false, so s is not equal to hello world. The second one is true, so s is larger because it also has additional string. And the second one, so s is larger than or equal to hello world, so that comparison is true. And the last one is false, that is s is not less than or equal to hello world. Under the hood, text strings are conventionally interpreted as UTF-8 encoded sequences of Unicode code points, which are values of type rune or int32 in Go. Recall that rune is an alias for int32. The UTF-8 encoding of a non-ASCII code point requires 2 or more bytes. Hence, the bytes of a string are not necessarily the characters of the string. For example, assume the string variable s is assigned to the string literal hello, space 世界, where 世界 is the two Chinese characters meaning word. The space character before 世界 is at index 6 in the string s, so the Chinese characters 世界 occupy bytes from index 7 in string s. When we print out 3 bytes at index 7, 8, and 9 of string s separately, it shows the 3 bytes in numbers 228, 184, and 150, respectively. When we try to print out the substrings, the substring s7:8, which consists of just the byte at index 7 in the string s, then it prints out the interpreted text of the byte at index 7 instead of the numeric value of the byte. Similarly, when we try to print out the substring s7 to 9 and s7 to 10, then it prints out the interpreted text of the bytes in the substrings. As you can see, the interpreted text for the substrings consisting of just 1 or 2 bytes starting from index 7 of a string s do not correspond to any Chinese characters in string s. But the interpreted text for the substring consisting of 3 bytes from index 7 of string s corresponds to the first Chinese character in the string s. This means that the first Chinese character in string s consists of 3 bytes in the string s. In order to understand the output of these statements, we need to learn a little bit more about Unicode and UTF-8 encoding. What is Unicode? Unicode is a collection of all characters, including those in all of the world's writing systems. Each character is assigned a standard number called a Unicode code point. Unicode version 8, which was released in June 2015, defines code points for over 120,000 characters in well over 100 languages. But how to represent these characters in computer programs and data? We could represent each Unicode code point with an int32 number. This representation is called UTF-32. In other words, UTF-32 is an encoding of Unicode code points as 4-byte sequences. This is simple and uniform, but it uses much more space than necessary because most computer-readable text is in ASCII, which requires only 8 bits per character. All the characters in widespread use still number fewer than 65,536, which could fit in just 16 bits. So can we do better than UTF-32? And the answer is yes, and that was why UTF-8 was invented. UTF-8 is a variable length encoding of Unicode code points as bytes. It was invented by two of the creators of Go and is now a Unicode standard. UTF-8 uses 1 to 4 bytes to represent each rune. Recall that rune is the Go terminology for Unicode code point. So when I say rune, it's the same as saying Unicode code point. Okay? So in UTF-8, only 1 byte is used for ASCII characters, and 2 or 3 bytes are used for most runes in common use. And so here's the patterns of the encoding. The high order bits of the first byte indicate how many bytes to follow. In particular, a high order 0 in the byte indicates a 7-bit ASCII. So it's identical to the conventional ASCII code. And for the runes that are represented with 2 or more bytes, the leftmost bit will be 1 instead of 0. So when the leftmost bit is 0, so that means that it will use only 1 byte to represent that rune, and that corresponds to the ASCII code character. A high order 110 bit indicates 2 bytes, and the second byte begins with 10. This 2 bytes encoding sequence represents values from 128 to 2047. So the values under 128 are not used in this encoding. So note that 2047 is equal to 2 to the 11 minus 1. So 2048 is equal to 2 to the power of 11. Okay. And the high orders of 1 1 1 0 in the the first byte indicates a 3-byte sequence, and in the two subsequent bytes we start with each will start with the 2 bits 1 0. Okay? And these 3 bytes represent runes of values from 2048 to 65,535, which is equal to 2 to the power of 16 minus 1. And the values below 2048 in this 3-byte sequence are not used. Okay? So this one also represent up to 65,535 runes. So those covers the most widely used Unicode code points. Okay? And the rest are used for all other runes that are not used frequently. Okay? And they must start with the first byte with the bits 1 1 1 1 0, and then in each of the subsequent byte we start with 2 bits 1 0. Many Unicode characters are hard to type on a keyboard or to distinguish visually. Unicode escapes in Go string literals allow us to specify those Unicode characters by their numeric point value. A Unicode character can be specified by Unicode escapes in 2 forms. The first form starts with \u and followed by 4 hexadecimal digits. The second form starts with \U and followed by 8 hexadecimal digits. The first one can be used to specify any 16-bit rune value, while the second one can be used for any rune value. Each escape in either form denotes the UTF-8 encoding of the specified code point. It does not denote the specified code point, but the UTF-8 encoding of that specified code point. For example, the following 3 characters are equivalent. That is the Chinese character Xi, which is the first character of the Chinese word for word, has the UTF encoding of the value in hexadecimal digits 4E16. Okay, so it is a 16-bit rune value. So you can use the first form, which is \u. You can also represent it as 32 bits rune value by adding 4 hexadecimal digits before the 4E16. Right. So this is the encoding, the UTF encoding of the Unicode code pointer for this Chinese character, which we don't need to know. We don't need to know the value of that code point, but we just need to know the UTF-8 encoding of that code point so that we can represent it using the Unicode escape like this one. And note that a rune value less than 256, which is equal to 2 to the power of 8, may be written with a single hexadecimal escape, such as \x and then followed by the decimal value. So, followed by the hexadecimal value. And so here the hexadecimal value of 41 is the ASCII code for the character capital A. Note that the ASCII code for capital A is 65, if I remember correctly. And when you convert 65 to hexadecimal, it is 41. Right? But note that the higher values must be represented with a backslash little u or backslash capital U escape. There are two forms of string literals in Go: raw string literals and interpreted string literals. The strings that we have used in examples so far are interpreted string literals. They are character sequences between double quotes, as in the string hi, like this one. Raw string literals are character sequences between back quotes, as in full, like this one. Within the back quotes, any character may appear except the back quote character. The value of a raw string literal is the string composed of uninterpreted characters between the quotes. In particular, backslashes have no special meaning and the string may contain null lines. Carriage return characters, which is denoted by slash or, inside raw string literals are discarded. Here are examples of interpreted string literal and their equivalent raw string literals. In the first two examples, located in the second and the third columns from the left of this table, the sequence of characters within the double quotes is the same as that within the back quotes of the equivalent raw string literal, because the characters in the double quotes in these examples do not contain escape sequences. In the last two examples, located in the two rightmost columns of this table, the interpreted string literals contained escape sequence such as double slash n, and slash double quote. Those escape sequences are represented as the raw characters in the raw string literals. For example, the double slash becomes just a single slash, and the slash n becomes the null line character, and the slash double quote becomes just the double quote character. We have learned the basics of strings and the use of Unicode in Go. Go also provides several standard packages for handling strings and Unicode. The first package is package strings, which provides functions for searching, replacing, comparing, trimming, splitting, and joining strings. The second package is package strconv, which provides functions for converting Boolean, integer, and floating point values to and from the string representations. Package Unicode provides functions for classifying rule values, such as a function is digits, which is to check if the given rule value is a digit, and function is letter, which is to check if the given rule value is a letter. Function is upper, which is to check if a given rule value is an uppercase letter, and function is lower, which is to check if the given rule value is a lowercase letter. Package Unicode also provides a function for converting to uppercase or to lowercase letter. Package Unicode/UTF-8 provides functions for encoding and decoding rule values as bytes using the UTF-8 encoding. So thank you for listening, and I hope that you understand the materials in this lesson.